Yo, stuff. Hey y'all, it's lesson 36 time. Writing and solving proportions. Writing and solving proportions. Righto, here we go. Let's define some terms. I got a whole bunch of things to say here about why this is important. We're going to do some proportional reasoning. This happens all the time in the real world. You know what that is? Oh, you think? I do proportional reasoning when I'm doing reading. I'm pretty dorky. I keep track of all the books that I've read. I keep track of how many pages I've read, how many books I've read every year, and I keep kind of like get competitive with myself. So I want to beat my like best total, 14,000 something pages in a year. And so I kind of look at where I am, and by the time I hit the middle of the year, I see if I'm halfway or not. And I think if I keep up at this pace, how many pages will I have read by the end of the year? Kind of dice it up by day. If I read at least 30 something pages a day, I can meet this goal. And so that's proportional reasoning. I'm thinking if I've done this much in 3 months, then I could do this much in 12 months. Do it too with running logs. How far am I getting toward my goal? How many miles a week do I need to do? That kind of stuff. Drawing maps uses proportional reasoning because there's always this scale at the bottom that shows you how close things are to each other and how much 1 inch represents on the map in maybe miles. So you got to do this in architecture and construction as well because you draw a smaller scale picture of what you're doing and then you use that picture of your house or whatever to then go and build the big size thing, or building models. Used to do that, get one in the mail. So using scale models and similar figures. Similarity here has to do with that the shape and the angles and stuff are all going to be the same, but the size is going to be different. So I was taking this card here, and if I hold it really close, it looks really big, right? But if I back it up, I get to the place where it's just barely fit it in there. There we go. It's the same size there as that box that I drew behind it. So if I bring it all the way up to it, you can see that though they are similar shapes, they're not same sizes. It's like people and paper dolls, right? They're similar shapes, but their proportions are different, right? Their proportions are different, even though they're sharing some things in common. One of those words for sharing things in common, well, we had similarity being the same shape but not necessarily the same size, is this word in math called congruent, or some people say congruent. And let me read the definition of congruent or congruent in the dictionary. Mathematically speaking, coinciding exactly when superimposed. Or having a different, that's something different. Corresponding. Coinciding exactly when superimposed. That's what I was doing with this. If I put one on top of the other, they've got the same shape, but not necessarily the same size. But things that match up. The angles match up. The proportions of the sides match up from the small one to the big one. So here's congruency with triangles. If you've already taken geometry, you know a little bit about this. That as long as those angles match, then the size is just basically scaling up or scaling down by some type of multiplier. I picked an easy one, a 3, 4, 5 triangle, and then this triangle has the same angles. They correspond. They're congruent. And then their sides then have to be matching as well. So what we do is we've got to make up here a ratio, a proportion. And that would be we start off with 3 on this triangle. And we're going to go to 6 on the other triangle. So if I was going to figure out what this side is right here, I would start with the fact that 3 to 6 is going to be the same ratio as 4. Let's call this side x. And now we've got some tools to apply to that type of problem. We can do that cross multiplication, what they call the cross product property. We can go 3 times x is equal to 4 times 6, and then finish that off. This is sticky note math. 24 divided by 3 is 8. Doesn't that make sense then? 3 is to 6 as 4 is to 8. And we could figure out that last one by doing the same thing. 3 to 6 is the same proportion as 5 is to y. And so, you can see that this is 1/2. So we're like, well, half multiply 5 by something. Here we can figure this one out pretty quickly. One way to think about this is that we're looking for some type of multiplier. Gets us from 3 to 5, that in the same way gets us from 6 to 10. So think of it like this. 3 times something, which might be called a constant of proportionality, equals 5. So we can do that. We can figure that out really quickly, that it's 5/3. And so if I multiplied 6 by 5/3, I would get 30/3 or 10. So that's another way to think about these proportionality types of problems. If the angles match up, then the sides, if they're the same shape, then we can find the other parts that are missing by using proportions, proportional thinking. Sometimes this is just a scale factor, and so there I was looking for the thing that turned one thing. This scale up to that scale, or this particular ratio here being the same as that particular ratio. It ends up being that's trigonometry. Here, let me do this another way. Okay? Do this one more time with this particular problem right here. Let's take 2 sides on this triangle and 2 sides on this triangle and compare them that way. Let's go that this ratio here, 3 is to 5. Okay? 3 is to 5. As, what's the same over here? As 6 is to y. If we take pairs of things in this one and compare it to the same pair of things in this one, basically we're trying to find out what is the scale factor. What multiplier do we use on this triangle to make it, just size it up and make it that triangle? Okay, so we're looking for, we put in here times the scale factor. It has to be the same scale factor for this top part as it is for the bottom part. 3 times what scale factor equals 6 is going to be the same thing as 5 times that scale factor equals y. And it's pretty obvious here that the scale factor is 2. So we can very quickly say 5 times 2 must equal 10. And we look at this, and this is still true. 3 is to 5 is 6 is to 10. Those are the same proportions, just scaled up. So scale factors can be used by taking a pair of things on one picture and then comparing it to a pair of things on the other. They're going to use triangles. They're going to use, all kinds of different shapes to give you scale drawings of these things and scale factors of these things. Scale drawings are drawings that reduce or enlarge the dimensions of an object by a constant factor, the scale factor. And scale is just the ratio showing the relationship between a scale drawing or model and the actual thing. So when I was a kid, I used to get these models in the mail, either like a car or a plane or something like that. And you put it together and it would be something like a 55 Chevy. And in the box it would say, what you're getting is a 12-to-1 scale factor thing. This is 12 times as small as the actual thing. If you took all the dimensions here and you multiplied everything by 12, you'd get the full size shape for this particular car. So a variety of things there, but mostly they're going to give you pictures, and then they're going to say, okay, scale it up or scale it down, or they're going to give you dimensions on a map. Here's a problem out of the reteaching. Look at number 3 here. G family is planning a trip from Dallas to Atlanta. On a map, the distance between the two cities is 9.75 inches. If the map scale is 1 inch is equal to 80 miles, what is the actual distance between the two cities? Okay? On the map, it's 9.75 inches between the two, and every 1 inch represents 80 miles. So what do we do here? There's a couple ways that we could format this. And one is we could stick with that 1 inches to 80 miles business. 1 inch, 80 miles. And then we're looking at in the problem, 9.7 inches is what we really got. So what are the number of miles? That's one valid way to phrase that one as an equation. Another valid way is to say, well, we had 1 inch, now we have 9.75 inches. 1 inch represents 80 miles, so x represents the distance, the actual distance between the two of them. The 9.75 gets scaled up in the same way that 1 gets scaled to 80. So you can see right there, this one's looking at it in terms of what's the scale factor. And we would multiply the top and the bottom by the same thing. 1 turns into 80, so 9.75 would be multiplied by 80 as well to get this answer. Over here on this side, you could use cross multiplication, but you end up doing very similar math between the two of them. But I just want to show you that both of those methods are 100% valid. It just depends on which things you're comparing, and so that gives you a little bit of creativity with the math to solve this problem in more than one way, as long as you're comparing the same things, the same types of things. Lots of things like that. Yeah. So if you look kind of toward the end of that lesson, we do have another thing there about ratios of perimeter, area, and volume of similar figures. And this one's pretty important because this is about shapes. Lengths of sides, areas, and then volume. That's going from one-dimensional to two-dimensional to three-dimensional things. And so the rules here are that if you're dealing with perimeter, your scale factor is A compared to B. One side compared to the other side. But once you bump it up and start talking about areas, you've got to square those. You got to take your scale factor and you have to do it twice, both numerator and denominator. And when you go to volume, you've got to triple that, or you got to cube that thing, a cubed to b cubed, because that's a over b cubed. A over b times a over b times a over b. Okay, so we're talking about 1, 2, and 3-dimensional things, so that if the scale factor would be, let's say it's 3 to 2, between one side and another side, their perimeters are in ratios of 3 to 2, but the areas of these two shapes would be in the scale factor, or the ratio of 9 to 4. And their volumes would be in the scale factor of 27 to 8. Okay, so the proportions are changing as we are changing dimensions. Super important as you're scaling up or scaling down. Like if we were going to have, we had a little plastic elephant and we were going to go up, we would say like maybe we're measuring its volume and seeing if that's even possible. And so if we would scale that thing up, we might find out that it's way out of proportion and that no elephant could possibly have that type of volume. Might mean that the little one has got some wonky dimensions. So this one's pretty useful. They use this when they're talking about dinosaurs and they're talking about if you made a model, could you actually build the real thing, or is your scale factor all messed up? Okay, so take note of that. Going from 1 to 2 to 3 dimensions, we have to either square or cube. If we're at area, it's a square thing, and cubic is volume. We've got to do that 3 times.